Voice assistants are the hottest thing in AI right now. OpenAI has just strategically released their new GPT-4o multi-modal voice assistant preview one day before they knew Google was going to release theirs.
It is very clear they are hungry for it. Savage.
While we wait for the bureaucracy of these tech giants to finish up their code, I'm going to show you how to code your own low latency, multimodal AI voice assistant. But before we get into the code, let's introduce you to your new AI voice assistant. Jarvis, I'm home.
Welcome home. How was your day?
Jarvis, it was great. I got some code pulled up on my screen. Can you tell me briefly what this program is?
It looks like you're working on a voice assistant project in Python. The code appears to be a comprehensive framework for building a multimodal AI voice assistant, incorporating various functionalities such as processing voice prompts, image and webcam input, clipboard text, audio input, and speech output. Is there a specific part of the code you'd like me to explain or help you with?
Jarvis, yes, I copied the program's entire code. Can you tell me what library this program is using for text-to-speech?
The program is using OpenAI's TTS-1 model for text-to-speech functionality, which is called through the speak function.
Jarvis, what do you see in my webcam?
It looks like I see a webcam capture of a male adult smiling and giving the middle finger, wearing a brown shirt and gray beanie. The background appears to be an attic with various objects like a microphone, cables, tape, and insulation. The overall tone of the image is coming across as rude and possibly intended to be disrespectful.
Y'all don't ever disrespect me looking like Blanche from the Golden Girls, you heard?
Now that Jarvis has introduced herself, let's jump straight into the code tutorial. First, create a folder to put your voice assistant files. Open your voice assistant folder in a code editor. I will be using VS Code for this video. Inside your projects folder, start by creating a file called requirements.txt. Open that file and copy the list of dependencies the same as mine. These will be the dependencies that your Python program will need for this voice assistant. Save this file and exit out of it. For those of you that do not have the patience or the desire to go through a Python programming tutorial video, which is exactly what I'm aiming to make with this video, you can access the source code to all of my videos in the Pro membership channels of my Discord. Having access to the Pro channels is not necessary to go through this video tutorial, as I will be showing all of the code for the voice assistant in the demo in this tutorial. Anyone a part of my Pro membership not only has access to my source code from this video and all of my other tutorials, but also a Pro written tutorial before I even release the videos. Videos like this take a lot of time to create with this much editing, which is why I'm able to release Pro written tutorials like this one before I can get a full video tutorial on my YouTube channel. To join the AI Austin Pro membership, click the Buy Me a Coffee link in this video's description. If you don't already have Python 3.11 installed, you'll need to install that on your computer for this voice assistant. With Python 3.11 installed, I can now open a new terminal inside of my project folder and run this command to install every library in the requirements.txt file. Make sure you don't get any error messages in this important step. If you do get any error messages and don't understand them, just paste it into ChatGPT and ask for an explanation of what is causing the error and what you need to fix it. If you get any errors specifically related to Pi audio on a Windows machine, you're going to need to download the wheel file and install it with that instead. These wheel files can be found at pypi.org, which is the official Python package index. Click on the download files, then find the files with CP311 in the name. These are the correct wheel files for Python 3.11. Now figure out if your Windows machine is a 64-bit or 32-bit processor, and download the file with the correlating number at the end of the file name. Once the wheel file has been downloaded, copy the entire file path to that wheel file. Now open Command Prompt as administrator and type pip install and then paste in the full path to your wheel file for Pi Audio. We'll now need 3 API keys. Get your Groq, OpenAI, and Google Gen AI API keys at these links and store them somewhere secure. The OpenAI API key will be used to create text-to-speech with their API. If you don't want to pay to use this program, you can skip this, and I'd recommend using the Pi-TTS X3 library to get free local text-to-speech. Using Pi-TTS X3 will not give you as high quality of a voice as paying for OpenAI, which is why I am showing it in this video, because a lot of people are demanding a voice assistant with a realistic human-sounding voice. Personally, I use Pi-TTS X3 for my own voice assistant because it gives me faster responses and I don't need that high quality of a voice. If you just want a clear voice, go with Pi-TTS X3. Inside your projects folder, create a file named assistant.py. The first step we want to accomplish inside of our Python program is creating a function to generate responses from Llama3 70B with Groq's API. We'll start by importing the Groq class from Groq. Then initiate the Groq client by passing your API key to the Groq class inside quotes. Define a function called Groq prompt that takes prompt as input. Inside the function, create a list called convo with the prompt formatted correctly for Llama. In another variable called chat completion, call the Groq client to create a response, passing the convo list and specify the Groq API to use the Llama3 70B model. Inside a variable called response, I will select the last message from Groq. Then we'll return the response.content from the Groq prompt. Outside of the Groq prompt, you can create a variable called prompt and request a text input. The program will store the return value from running our Groq prompt with our text prompt input. And now print the response content to the terminal. If you've installed Groq correctly and set your API key in the parameters, this script should allow you to prompt Llama3 70B from the Groq API. This Groq prompt will be the main function for our conversation with our voice assistant. If you have not already heard of Groq yet, Groq is a company that invented a new piece of hardware that is like a GPU, but specifically made for inferencing language models. This allows for us to get high speed, aka low latency responses from the Groq API, even using a 70 billion parameter model. But we're going to need much more than a conversation with the language model to make this AI agent fully multimodal. We now need to create a function to call functions in our program from the language model. Define function_call that also takes prompt as input. Inside this function, we will create a system message variable. Write the system message string the same as mine here. If you want to add any new function calls, specify the function in the first sentence and the list at the end of the system message text string. Underneath system message, we'll structure the function conversation with the system message and the prompt from the user. Back up at the Groq prompt, we can copy chat completion, response, and return response.content, then paste that into function call. Then change convo in the chat completion input parameters to function_convo. Above the response variable outside of our functions, we will create a function response that sends the prompt input to our new function, and we can print that function response. If you did add any new function calls to your program, now would be a good place in the tutorial to test your system message is actually getting Llama to call your functions reliably. Now we have our code to communicate with the main brain for our assistant through the Groq API. Let's add our 3 functions to take screenshots, take photos, and extract text we copy for the assistant in our conversations. The take screenshot function will need us to import the ImageGrab class from PIL. Inside the function, we will set the file name for our screenshot captures. Create a variable screenshot that stores the raw image data from calling ImageGrab's grab function. Create RGB_screenshot to convert the raw image data to RGB format with the ImageGrab's convert function. Lastly, for this function, we can call the save function on RGB screenshot by passing the path and setting the quality to 15%. Dropping the image quality to 15% will allow for lower latency when prompting the image processing language model we will implement later, and allow the language model to process these images faster. If you want to test the take screenshot function, create a new file called test.py, paste the function and import statement for image grab. Call the function on the last line of your program, and once it finishes running, you should have a screenshot JPEG file in your voice assistant's folder. Once your screenshot function is working properly in your test file, make sure the code is the same in your assistant file minus the last line in test.py. Delete all of the code in test.py and import CV2 that we will use to allow our program to take webcam photos. We'll write this code out in the test function to make sure we are calling the correct camera on our computer. Create web_cam that equals cv2.videoCapture. Pass 0 as an input variable. 0 is specifying the camera number in the list of available cameras on your computer. Even if your computer only has one camera, CV2 might think there is more. So let's first test it at 0, which is most likely your device's webcam. 0 is specifying the first camera in the list. Define webcam capture, and on the first line, check if not webcam is opened, which in English means the program has not successfully opened a camera on line 3. Print a message letting us know the camera was not successfully opened and exit the program. On Mac or Linux, this will not occur if you have installed CV2 correctly, and when first running the program, grant your command line app permissions to access the webcam. For Windows users, it is possible you will need to manually grant permissions for command line to access the web camera. If the program doesn't quit, our program is successfully opening a camera. So outside of the if statement, we can create a path variable to store the name of our webcam photo. We'll store ret and frame from calling CV2's read function on our webcam. We can now save the webcam photo with CV2's write function and call the function on the last line in our program. Run test.py and make sure the webcam.jpg file is in your voice assistant's folder and capturing the webcam. If the webcam photo is not actually your webcam, try changing the number input to the video capture function +1 until you find out which number in the list of CV2 cameras is actually your webcam. Once your code is functioning, copy it into assistant.py and make sure you import CV2, then save assistant.py. Our get clipboard text function will need paperclip imported. Inside the function, create clipboard_content that will store the results from calling paperclip.paste. We can now use an if statement to check the results for Python's built-in isInstance function's results for clipboard content, specifying the variable should be a string, meaning text content. If there is a string, we will return clipboard content. Else clipboard content is not a string, so we will print to the terminal, letting us know we probably didn't copy the text correctly, and return none as the context for our prompt. To test this function, you can delete all the code in test.py and replace it with import paperclip in your get clipboard text function. Then you can print the results of get clipboard content, which should display the text that you copy before running test.py. Now we can implement Google's new Gemini 1.5 Flash model for low latency image processing. As stated earlier, we'll be using Llama3 through the Groq API as our main model for our voice assistant. We'll simply use this new Flash model to provide low latency, highly relevant context to our voice assistant. First, import Google Generative AI as GenAI, also PIL's image class. Next, configure your connection to GenAI by passing your Google GenAI API key. We can now set up our LLM configuration settings for Gemini, then turn off all safety settings by setting them to block_none in all caps. Then we can set a model variable to load the Gemini Flash model with our config and safety settings. Define vision_prompt that takes prompt and photo path as input. Inside IMG, open the image at photo path. Then we will format our prompt with a prompt heading and add the prompt input to the end. Inside response, we can generate a response from Gemini Flash by passing the prompt and image input formatted in a list. Finally, return response.text. Now let's start wrapping everything together and make the program conversational with the ability to call our functions and send images to Gemini Flash if necessary. First, create a system message for our Llama3 conversation. Then we can format the system message in a list called convo. Now delete these lines after the functions and create a while true loop. We can request the text prompt input, then inside call, store the response from function call. If take screenshot is in call, print taking screenshot and call the take screenshot function. Inside a variable called visual context, store the response from sending the prompt and image path to vision prompt. Else if capture webcam in call, print capturing webcam and call the webcam capture function, then again send the prompt and photo path to vision prompt. Else if extract clipboard in call, print extracting clipboard text, inside paste, store the returned text from calling get clipboard text. Then modify prompt to have 2 line breaks after the current prompt, tab, then all caps, write clipboard content, and add the pasted text. This format will help Llama better understand the prompt from the pasted text. Then we can modify the Groq prompt function a bit to handle a conversation instead of a single prompt. First, let's add img context as an input parameter. Delete the current convo since we created one outside the function to track our Groq conversation. Check if image context, then format the prompt with the image context. Again, putting 2 line breaks, a tab, then writing in all caps image context before adding the image context to the prompt. Now we can add that formatted user prompt to the convo list with Python's append function. After response, add the generated response to the conversation. Back down inside of the while true loop, create response that will equal the results from sending the prompt and image context to Groq prompt. Then print the response at the end of the while true loop. Now we've been through a lot of code. This is a good point to check that all of your code is the same as mine at this state in the tutorial. Then, once you have all your code matching mine, you should be able to have a conversation with your multimodal AI agent. With that working, let's give our voice assistant a realistic human voice. For converting text to speech, we will import the OpenAI class from the OpenAI library, and also import Pi audio. Below our Groq and Gemini API configurations, we will create OpenAI client and initiate a connection to the OpenAI API by passing our OpenAI API key. We can now define speak that takes text as input. Since I have explained this code already in another voice assistant video, I won't go too in-depth on this, but this is the optimal code for streaming text-to-speech from the OpenAI API in Python. What you do need to know about this code is the voice parameter is where you can choose one of 6 OpenAI voices that you prefer for your voice assistant. Here's a quick sample of each voice.
Hello world, I am Shimmer.
Hello world, I am Nova.
Hello world, I am Onyx.
Hello world, I am Fable. Hello world, I am Echo.
Hello world, I am Alloy.
Once you have your speak function complete, inside of the while true loop, you can call the speak function after printing your response, and your program will now have a high quality, low latency AI generated voice using the OpenAI API. We now have given our assistant multimodality and a voice. The last step is to allow our program to efficiently handle voice prompts and a wake word. Unlike OpenAI, we are going to set up a wake word for our voice assistant because unlike the GPT-4o voice assistant, we want this program as something we can start up when we are next to our computer and the program is always waiting for us to intentionally send a prompt. A voice assistant shouldn't need us to open the program, click start listening, wait 8 seconds for the GPT-4o model to load, then start speaking a prompt. Instead of having to wait 10 seconds to talk to our AI friend, we're trying to create a voice assistant that is always ready to respond to our prompts when we need it and not making noise in the background when we don't. At the top, we import OS and from Faster Whisper, import the Whisper model class. We will set num cores to check how many CPU cores your device has. Then we will set Whisper size as base. In Whisper model, we will initiate the Whisper model class on CPU with int 8 and set the CPU threads to equal half our total CPU cores and the num workers to equal the same. Define wave to text that takes audio path as input. Set segments and underscore to store the results from calling Whisper model's transcribe function on our audio path. Inside text, we can join the streamed results from Faster Whisper. And lastly, return all the transcribed text. Now that our program can transcribe audio, let's implement some code for the program to process audio in the background process to keep latency as low as possible. Import speech recognition as SR and the time library. Set wake_word as your wake word. I'll use Jarvis as mine. Set R to initiate SR's recognizer class. Then set source to initiate your microphone. Define start listening, and with source as S, call the recognizer's adjust for ambient noise function to analyze microphone input for 2 seconds when the program is starting. Print a message to the terminal telling us we can say the wake word followed with our prompt to notify us the program has finished starting up. Then call recognizer's listen and background function, passing our microphone source and callback as input, which is a function we will define later to control what the program does based on the audio input. Then in a while true loop, we will sleep the program every half second, which stops the callback function running in the background from overworking our CPU. In all of my previous voice assistant tutorials, we have handled wake word detection by having the program wait for the user to speak just the wake word, respond to the user that the program is now ready to record a prompt, and then start recording a prompt. The previous method was easy to code, but honestly annoying to use. In this assistant, we will implement a more modern approach of having the user just speak the wake word immediately followed by the prompt. This will bypass the wait period between recording a wake word and then the prompt, which is a much more intuitive way of interacting with an AI voice assistant in 2024. Now that's the theory behind how we will handle wake word detection. To implement this in our code, we will import RE, which is Python's regex library. Then define extract prompt that takes transcribed text and wake word as input. Create a variable called pattern where we will write this cryptic regex code, setting the format to search for in our transcribed text to find the wake word and the text following. While regex notoriously has the ugliest syntax in anything you could ever write with code, it is a highly efficient way to handle string search in Python. Inside match, we can call regex's search function, passing the pattern, transcribed text, and re.ignore case as inputs. We can check if a match was found in the search function. If so, we can set prompt to select the text after the wake word in our match and return the clean text prompt. Else there was not a match in the transcribed text, so we will return none. Now we just need to set up a callback function to control the logic of our voice assistant and how it will act depending on what we give it as voice input. First, delete this current while true loop in our program. Define callback that takes recognizer and audio as input. Set prompt audio path to prompt.wave. Now we can open the prompt.wave file, whether or not it exists yet, and write the audio input to the wave file. In prompt text, call wave to text on the new audio file to transcribe the voice input to text with Faster Whisper. With clean prompt, we can store the results from extract prompt. If clean prompt, which basically tells us there was a wake word and following prompt found in extract prompt call, then print the user's clean transcribed prompt to the terminal for visual feedback that the program understood us. Inside of call, pass the clean prompt to function call. Then we will run through this if sequence to check whether a function call needs to be performed and handle the context from a function call accordingly. After checking for function calls, we can generate a response with the visual context and print the assistant response to terminal. Finally, we can speak the response from our multimodal voice assistant. Now our program has all of the code it needs. We just need to call start listening to effectively start up all the processes and have our voice assistant ready to respond whenever we speak the wake word. If you guys appreciated this Python tutorial, don't forget to hit the like button on this video and subscribe for more practical AI videos like this.